Okay. So if we have losses in these transmission lines, I apologize for those of you, we just do a review today of what we have seen so far in transmission lines. And then all of the notes are online. So if you have losses, there are two types of losses. There is a conductor loss that happens in the wires or in the conductors. And there is a dielectric loss that happens in the material that separates the conductors. Two conductors have to be separate. All right. Usually you have to, if you have to have dielectric to keep them separate. And if we are printing them, because that's what we use transmission lines in high frequencies, all right? If we are printing them, we print them on a dielectric. And whether they are on each side of the dielectric or they are on the same face, side by side, they still have a dielectric. And the dielectric may have dielectric losses. So usually that comes into the form of the conductance, which is in parallel with the capacitance. All right, because you have the capacitance like this, the conductance is the better way to put the loss in here because it has the same units with the J omega C, the capacitance we see in the Phasor domain. All right. Yeah. So here, for example, I will need to put the J in there because this is the right way to do it. Let me see. J. Okay. And what we said last time and we stopped there is the loss inside the conductors is characterized by a conductivity, sigma. And the higher the conductivity, the more the losses, all right? So ideally, you would like to have, what did I say? The higher the conductivity, the lower the losses, all right? So ideally, you would like to have the conductivity of the conductor to be infinite, which means infinite conductivity allows all the free electrons to move without losing energy as they try to move on the surface of the conductor. Infinite conductivity, first of all, implies that the current, all of the electrons will flow on the surface of the conductor, and nothing is going to happen inside the conductor, not going to be any electrons flowing, any current, any field, all right? So all the electrons, all the charges on the surface of a perfect conductor. Perfect conductor has infinite conductivity. When we go to the dielectric that separates the two, we want the dielectric to have zero conductivity. We don't want any free electrons to move through the dielectric, because if there are free electrons that can move through the dielectric, then you have this filament of currents that flow in. Small current that flows, not too many electrons, but if it flows from here down here, you lose the energy. All right, so you lose energy inside the dielectric. So we want to have the conductivity of the dielectric to go to zero, and the conductivity of the conductor to go to infinity for losses. All right. So now I wanted, since you saw that in your homework, you saw in the homework when you try to get the formulas to write, to find R, because copper is conductive. I mean, it's not perfect conductor. There's no real metal that's a perfect conductor, right? Some are better conductors than others. So they have higher conductivity than others. However, copper has a conductivity which is 58, 10 to the 6 Siemens per minute, Siemens per meter. And what that means, since it's not is very large, but since it's not infinite, it means that instead of all of the charges and the currents to be on the surface of the conductor, there is a small current that flows inside the conductor. And how it flows inside, you can see it here. It has its maximum value on the surface of the conductor, and then it goes down exponentially. And it goes down exponentially as e to the minus a, the distance from the surface, where now a is the inverse of a quantity that we call it the skin depth. All All right, so the smaller the skin depth, which is a measure of the depth here, the higher the alpha, which means the faster the way the current goes to zero inside the conductor. So how do we define the skin depth? And that's since you're gonna hear it, you define the skin depth as the depth where X becomes delta, where this alpha X becomes 1. So it becomes e to the minus 1. That's how we define the skin depth. It's a standard that we develop so we understand. The higher the skin depth, the more the current that flows inside the conductor. And if a current flows inside the conductor, you lose energy. All right. So the lower the skin depth, the larger the alpha, the faster the reduction of the current as it enters the conductor, the lower the losses. Now, why the current inside the conductor loses results in energy loss? Because the electrons which are creating the current, all right, these are the charges that are moving. Inside the conductor, every conductor has the atoms arranged on some kind of a grid. And the grid is, unless there are impurities, the grid is pretty symmetric for every conductor. So they are steady there, they don't move. And they have their own electrons which are bound very well to the atom. So the electrons, these free electrons that come from the source, if they start flowing inside the conductor, and then they come into a collision with an atom here, if an electron comes in a collision with another electron, it has to change its direction. So practically, it loses energy at that point. Every time it's diffracted. So that's what we are trying to avoid by having perfect conductors where the conductivity inside is infinite, meaning practically that all of these free electrons are on the surface and they do not interact with these atoms on the grid. Okay, in a simplistic way. Of course, the physics is much more complex at that microscopic level. So now we found our equivalent circuit. This is still for a small, electrically small line. And from here, we are going to look at, well, this is what we have seen about the phasor domain. All right, so assuming that you remember that, how we introduce the phasors, because we are going to go away from the time domain and we are going to turn this equivalent circuit into phasor form. So if we have, as we saw last time, the equivalent circuit, if we turn it into phasor form, so R is the resistance per unit length, assuming that this is a unit length, all right? Or R times delta Z is going to be the total resistance for this section. J omega L is the phasor. This is with a J in front. This is also has the units of ohm. And for this length, which is delta Z, you have to multiply J omega L with delta Z. And then J omega C has the units of 1 over ohm per unit length. So if you multiply it by delta Z, it becomes J omega C times delta Z. That's going to become 1 over ohm. And it's going to be in parallel to the conductance. And this conductance also is going to be per unit length. So you would have to multiply by delta Z. We did this last time. And we came down to a set of partial differential equations. And those partial differential equations are here. All right, they are coupled partial differential equations. This one, in fact, has only L. It's only what happens. This is only an example, as a matter of fact. So let me find Okay, here we go. So these are the two partial differential equations, all right? So we derived last time. And here now we have R. We have eliminated, these are partial differential equations that apply in on a section of a transmission line, which is of unit length, but applies everywhere on all of these multiple sections. So you don't see R times delta Z or something. These are not total resistances or total inductances. These are still per unit length. So when we write the equations to characterize one infinitesimally short transmission line, they apply to the whole transmission line, all right? This is what happens with those equations. And in these equations here, R is per unit length, L is per unit length, G is per unit length, and C. If you, because eventually all of these delta Z's or these Z's that we had here multiplied by that, they all went here. All right. Now, we introduced two new quantities. Z naught, which we call the characteristic impedance. And this is the ratio of R plus J omega L. All of these have the units of ohm, divided by G plus J omega C. All of those have the units of 1 over ohm. So you have ohm squared as a unit inside the square root, which gives ohm for Z naught. So Z naught is an impedance in ohms. Complex impedance, because we are in the phasor domain. Beta. Beta now is in fact, I would prefer, even if you will see also used interchangeably, but I would prefer at this moment that we put this as gamma, and gamma here is called the complex propagation constant. Gamma complex propagation constant. Okay. Now, what happens in this, I will show you here, and then we are going to go back to the other. But this one, what happens when R is very small compared to J omega L, so your losses, conductor losses, are very small, very low, or is totally lossless, as we will see in all of the transmission lines we will see from now on will be lossless. Then R can be neglected, here can be eliminated, and G, if G, which are dielectric losses, are much smaller than J omega C, then we can assume that those two are going to 0. And then Z naught is going to be only the square root of L over C. And that is a characteristic impedance, and it is in ohms. So this one is in ohms. Okay, and then here, I will put gamma, which is J beta. All right, so now we are, and gamma is the square root of this, becomes G and R go to 0, so it's becoming minus omega squared LC, and then J omega square root of LC, which is J beta. This is what, either plus or minus, but we'll use the plus here, J beta, where beta now is called the propagation constant, not complex, the propagation constant. All right. And Z naught is called the characteristic impedance. And that's what happens when you have no losses. So now, with this in mind, and without losses, we can go here. And here is what I'm gonna do for a moment, and then I will erase some things here for a moment, and then I will bring them back. In fact, I'm not gonna erase them, I'm just gonna cover them. Okay, so I will do this and this. Matter of fact, this. I will remove that for a moment. And I will do this and this. So now we'll assume for a moment that our line is either infinite long, no. Our line is either infinite long, goes forever, or as we will see later, the line is matched. So in this particular case, we will consider that the line is infinite long. Now, what happens if the line is infinite long? We have, we have here a wave that is created by the source. All right, so the source is going to create a voltage wave, which we're going to call, we will indicate it with V plus. Whenever you see me writing V plus, it means the incident wave. And it shows that the wave is excited by the source. And then start going on this line. This is not in the time domain. This is space. All right, so we are on a one-dimensional space right now, where this is the z direction. So I will assume that this is the z direction. Okay, and there is no time because we are in the phasor domain. The phasor domain also, you know what it means? Steady state. In the circuit class, you may have heard about steady state. Well, steady state is nothing else but what happens in the frequency domain, all right? And then, so here we are calling phasor because everything, all of the entities are complex. But in any case, you get this as the incident wave. And this wave keeps going. It does not see anything else but the line itself. So it only exists as an incident wave, all right, and nothing else. And this wave is going to be in this form in the phasor domain. Practically, it's going to have an amplitude or magnitude because we are in phasor domain, a magnitude, and it's going to have a phase. So practically, the magnitude of the wave does not change, but its phase changes. And it changes linearly with the length by this constant. That's why we call it sometimes propagation constant or the phase constant. Sometimes you can hear it as the phase constant. So the amplitude of this is, the magnitude of this is constant. So if you were to show, even if we show it like that, it's like more visually understandable. It's even if sometimes we show like this, we don't necessarily mean it looks like this in the phasor domain. This is the real part of that. If I take the real part, if I go back to the time domain and I take to the time domain and I take the real part and yet freeze time, what I'm going to see along the length of the line is something like that. All right, that it would have been difficult to show just a straight line. And that's why we do this kind of thing, even if we are in the phasor domain. Okay, but the magnitude is constant. Now, in addition to the voltage, we have a current. You remember the two partial differential equations? We have two unknowns in these partial differential equations, the voltage and the current. And both of them are a function of z, of the length. So if you are here, the voltage and the current will be different. If you are at any other point, if you are in the beginning, for example, when z equals 0, the phase of the voltage and the current will be 0. If you go someplace here at z naught, both the phase of the voltage and the current will change by the same amount, but you are going to have a different phase from what you would have at z equals 0. And then at any other point on the line, the phase is going to be different, but the magnitude is going to remain the same. What happens now if instead of an impeded line, we have here, we have a load. You remember we talked about that this impedance at the end of the line is called the load. Then the wave, as it comes here, sees this load, and this load creates what we call a reflected wave. All right, so when the line is terminated and is not matched or infinite, the incident wave reflects, that's why I call it reflected, reflects off the load and creates this wave, which either you're gonna indicate it as B reflected or as B minus. And a lot of times we do that to avoid too many letters here. And if this is the case, then the reflected wave is gonna create, therefore, another voltage, the reflected voltage, which is going to have a different coefficient, and of course, a phase that changes with Z, but with a different sign. Pay attention to that. And then the current will do the same. A new coefficient for the reflected current and a change in the phase. And since both of them are created, then the total voltage and the current on this line is going to be given by this. Where now, what you will always find is V naught plus, which we found here in the incident, and I naught plus, they are not totally independent. They are related through the characteristic impedance. So if you find one, then you know the other. So in reality, we don't have 4 unknowns. We have 2 unknowns. We have V naught plus as an unknown and V naught minus as an unknown. If we find V naught plus, we know I naught plus. If we find V naught minus, we know I naught minus, because it's characteristic impedance, but with a negative sign. Make sure you pay attention to the negative sign, because a lot of us forget it. So now, we found the fundamental properties, all right, and the equations of a transmission line. Now I would like to show you an example where we are going to put all of this to practice. How are we going to do that? Okay, so let me do an example for you. So example. In the things that what you can solve with an ideal transmission line, and let me in fact here copy. I don't have it here, so I will do this. Let's assume always transmission lines will show them like this. Okay, and then we'll duplicate here, and then we are going to have only simple wires here like that to show simple connections. On one end, we are going to have a source. We are in phasor domain. The source is AC, but the magnitude of the source is B sub S, and we can say that this is 5 volts. All right, and then we have, let's assume that at the end, now is not an infinite line, but at the end, we have a load, C sub S, which is 50 ohms, practically the resistor, okay? And I give you a line, which is a 50 ohm line. 50 ohm lines, in fact, let me make this 100 ohms. Don't want to make them, next time we'll make them 50, 100 ohms. All right, and then Z naught here is gonna be 50 ohms. And then I have an operating frequency F, which is, say, 10 gigahertz, which in fact makes the wavelength 3. excuse me, gigahertz, not centimeters, I'm thinking. 3 centimeters in free space, okay? And let's assume now that this line here has a particular length. Let's assume that the length of the line is 1 wavelength, all right, which is 3 centimeters. This is the length of the line. Okay, let us now try to find the following. We would like, first of all, let's see what we know. In these problems, I just would like to remind you that when you have problems like that, put on the left what you know, and you would put on the right what you have to find, all right? So we know F, we know L, lambda, we know L. So the length of the line, so if here this is equals 0, and this is equals L, the length of the line is 3 centimeters. What else do we know? Beta is how much? 2 pi over lambda. All right, if we know lambda, 2 pi, we know beta. Okay, so you do that. Then what else do we know? We know that Vs is 5 volts. And we know that ZL is 100 ohms. What else do we know? We know the voltage and the current in the general form, all right? See, this is what we know. What we know. Here. Now, we know that V at any point Z on the line is gonna be equal to the incident wave plus the reflected wave. This is voltage. All right, and we know that the current is gonna be the incident current, e to the minus j beta z, plus the reflected current, e to the j beta z. However, because I have related, I have related V naught plus and I naught plus and V naught minus and I naught minus with Z naught, see how I can rewrite this equation is gonna be, since I'm writing here, Z naught equals V naught plus over I naught plus equals minus V naught minus over I naught minus. This can be written as 1 over Z naught V naught plus e to the minus j beta z minus V naught minus e to the j beta z. So practically, I have now 2 equations, all right? This one that I'm gonna change the color so you can see this. And this one. So this is how I would like you to set up your problems. If you do it carefully like this, the solution is gonna be easier after that. Okay, now. What do we need to find? To be able to find the voltage and the current, we need to find V of Z, and we need to find I of Z. All right, to be able to find that, how many parameters we need to know? Look at how many things we know and what we need to find. We know beta. Do we know beta? There. And we know lambda. All right, what else we know in this line that I have not written it, and that's you have to add. All right, so you see, there are 2 things that we have not implemented yet, and which we call the end conditions. The or the boundary conditions, the condition at the source and the condition at the load. These two conditions we have not included yet. So let me do that. And then as a matter of fact, as soon as I finish that, you will see that the result is gonna be easy to get. So what we have at the source, we know that V total, V of Z, when Z equals 0, equals, all right, is exactly the voltage that is applied at the input port. How much is the voltage that applies at the input port? 5 volts, right here. This is 5 volts. We know that. Therefore, from here, from this equation, V of Z when Z equals 0 is 5 volts. You can call it V sub S, is 5 volts. All right, so that is one condition. What else do we know at the load? What relationship do we have at the load? From Kirchhoff's, from Ohm's law, rather, the voltage across the resistor equals to what? The resistor times the current that flows through, all right? Ohm's law. So at the load, we have that V at the load, which is Z equals L, equals I, when Z equals L, the current that flows through the resistor times the resistor, the load. These are two more conditions we know. So practically, this is going to be I at Z equals L times 100. All right? So now we have two equations with two unknowns. And we have two conditions. So practically, I can take from here and put Z equals 0. And if I put in number 1, let me call this number 1. Here, this is 1 and this is 2. Let's assume that this is 3 and this is 4. From 1, what I have at Z equals 0, I have that V at Z equals 0 equals V naught plus V naught minus. You see that? If I put Z equals 0 here, that goes to 1, that goes to 1, so it's V naught plus V naught minus. And I have from the boundary condition at the source, which is number 3, that V naught plus V naught minus is equals 5. I have that. One equation. I'm going to get the second one from the load. So I'm going to go and put Z equals L. And then from 1, 1 here. And then I have from 1 and 2. When Z equals L, I have from 4 that V at L, which is going to be V naught plus E to the minus J beta L plus V naught minus E to the J beta L, and then I at Z of L is going to be 1 over Z naught, B naught plus E to the minus J beta L minus V naught minus e to the j beta L. And then the ratio of these two gives me Z sub L. So if I take the ratio of these two, I find from here that Z sub L over Z naught equals, I moved also Z naught there, V naught plus e to the minus j beta L plus V naught minus e to the j beta L divided by V naught plus e to the minus j beta L minus V naught minus e to the j beta L. So now I have two equations with two unknowns. All right. And then I can find from these two both V naught plus and V naught minus. This is, we are not going to do it as much because this, you go extensively only once, and then you remember when you have to do this, the equations are the same, no matter what you have. And as a matter of fact, also, as we start solving problems, you're going to see that many times we're going to simplify that even more. But this is one theory only that applies to all transmission lines. So there is nothing more to it in terms of theory. And then eventually you just have to find, always, from two equations, you need two boundary conditions. Okay, so with that, no exercise today. I will give you what I told you about this as it's gonna be combined individual, and I would like you to work also in teams, and team exam next weekend, the one that I told you that I gave to people for the makeup assignment, because there are 200 points. You're gonna do this three. I will split it, so 3 is gonna be individual and 3 questions will be team. All right, so I will set it up and then I will let you know, but it's gonna be the same questions that I had. I think it will be good as a review. Any questions on this? Okay, next time we're gonna also solve the quiz, all right, the board.